It's time to begin. First, a couple bookkeeping things. Number one is, remember that the second homework assignment is due today. It's due by 5 p.m. if you turn it on paper. Just stick it under my door in my office or give it to me. If you turn it in on Moodle, you have until 11:55 p.m. One thing to know, if I didn't make it clear, because I don't think I did, for the questions, you need to have reasons for your answers. If you just have, like on the last problem, you have calculating numbers. If you just have the number and you don't show the calculation or how you got that, you won't get credit for it. It needs to show how you got the values. Is everybody clear on that part? Because I don't like taking off points, but I want to see that the student knows how they got the answer, not just that they were able to find it by, flipping to the back of the book or whatever. So, homework today. There was one more reminder I was going to give you, but I don't remember what it was. So, let's move forward to this fun cartoon. What value would this cartoon have for this class? None.
His scientific reasoning to see what would happen if he put milk up his nose instead of just drinking.
Okay, this is a kind of scientific reasoning. There's one thing that's missing from our 4-step scientific, of the first 3 steps. One step is missing. What's the one step that's missing? He makes an observation, right? He says that milk comes out your nose if you laugh while drinking. So if it goes in your mouth, you laugh, it comes out your nose. And then what's the next thing he does? Starts with observing something interesting.
He makes a hypothesis.
He didn't really make a hypothesis, though.
He just declared his experiment.
He just declared his experiment, but didn't give the hypothesis part. Now this is a comic strip, it's supposed to be a kindergartner or whatever, so you don't expect it. But what he should have done if he was following the scientific method, instead of being a kid, just enjoying scientific inquiry, he said, okay, so why does it come out? And then hypothesize, well, there must be some kind of tube going between the nose and the mouth, and so you put it in one and it can come out the other. And then a test of that tube would be if you put it in your nose, is you come out your mouth. And then he's going to go and do his experiment. So it's almost perfectly the kind of thing. I won't give you that observation that when you laugh while drinking milk, milk comes out of your nose on the test. Just so you know, that won't be the observation. But it was reasonable. Now we're going to start talking about motion. And Sir Isaac Newton is one of the great people that we talk about with motion. And I always like this statement to see, we must stand on the shoulders of giants. He made the statement regarding his own advancements of science. It's not just, hey, I'm a great mind, I came up with all of these great discoveries. It's that we have to have, with the whole scientific process, we make our hypotheses based on already existing scientific understanding. And so, for his advances in science, and even his invention of calculus, he used the work that other people had developed for his base, and then just moved it forward. So he definitely did move things forward. There definitely is genius to his work. But without other people's work, it wouldn't have been possible. All right, so getting to the topic of the day, the motion, it's important that we understand what words mean with regard to motion. Now, I'm going to give you 3 successive clicker questions on the definitions of words to see how you understand them. But I'm going to define a couple before we start. So the first one, and these aren't even in my presentation because they're pretty obvious, position. Right. What is a colloquial definition for position? I'm just looking for a basic, way you would tell your kid if your kid said, "What does position mean?"
Where you stand.
Okay, where you stand. Position is where something's located. Now, in science, when we measure position, we do it with numbers, with units, because a number without units is fairly meaningless. What units do we use for distance in science?
Length.
Well, yeah, for length. What units do we use for length? The units are like meters, right. We use meters in science. Now, we may use prefixes or just prefixes, not postfixes. We have things like kilo, which means 1,000, or centime, which means 1/100th. But we measure in something that has to do with meters. Now, I say in science, back in the day, they used things like feet. But science has developed a nice factor of 10 system. So instead of having 12 inches in a foot, for instance, you just have 10 centimeters in a decimeter, 10 decimeters in a meter. Nobody ever uses decimeters, right? 10 decameters. Well, anyway. So, when I measure the position, I could say, for instance, that Tyler is 3 meters away from me. Is that, okay, take for granted that 3 meters is about right. It really is. See that long stick there next to Zachary? That's 2 meters, and the one next to it's 1. You add those two together, that's 3. It's about our separation. So, is it accurate to say he's 3 meters away? Yeah. Does that tell you exactly where he is? No. Why not?
It's not precise.
It's not, well, actually, you're right, it's not precise. But I was looking for something else.
Doesn't matter where you could be.
Yeah, he could be anywhere in a circle that's 3 meters away from me. Or, for all we know, he could be on the floor above me. The separation between floors is about 3 meters from the bottom of the floor to the bottom of the floor. So it doesn't tell you precisely where he is because we don't have the direction. So we will talk about position, and we will usually talk about position with directions. Like, my home is 3/4 of a mile that direction, right? If you were to just go 3/4 of a mile that direction, however you like to get there, you'll find my house. Now, that's not precise again. It's not exactly 3/4 of a mile, and my direction probably was not precise either. But we usually specify with direction and with the distance. We call a property or a quantity that has both the direction and the magnitude. Magnitude is how big it is, the size. We call those vectors. So we use vectors. Now, another term we talk about in physics is displacement. And in this regard, displacement will be the difference between the starting position and ending position. And to give a simple example of the difference between distance traveled and displacement, we all know what distance traveled is, right? How much ground has been under you as you travel. So if I start here and I walk around the desk, at this point we can say, okay, I've walked 4 meters. I keep going. Woohoo! What's the total distance I walked doing one lap if it was 4 meters over? 8 meters. So the distance I traveled was 8 meters. But the displacement is the vector, that is, it's got to have direction, that points from where I started to where I ended. 0. So in that trip, my displacement was 0 because I ended up where I started, even though my distance was 8 meters. So the two are different things. Those are going to be important ideas coming up, and of all the things I've said, probably the only thing that is reasonably new is that displacement part. Okay, so let's go to the clicker questions. Now I feel really stupid. Yep, feel really stupid. We do have some definitions here before the clicker questions. I thought they were right there. These are just setting you up. What are the differences between average speed and instantaneous speed? velocity and speed and acceleration. So those are things we're going to learn. So first, our clicker question, what is speed? So answer the one of these that you think is correct. Right? We haven't studied this. There's no shame in being wrong. Just trying to see what you understand.
What's the channel?
Channel 33. Only have 5 so far, and I actually don't have, so I can see who's answered. How many people don't have clickers?
Well, I have one, but it matters.
That means we should have 2 more answers then, because only 3 people raised their hands. Okay, got 6th one in. Well, I can't tell who it is, so I'm just going to move forward here. So our answers were 3, 2, 1, 0. Well, at least it's orderly. Now, we haven't studied this, but I'll tell you the correct answer now, even though it's going to come up again in the lecture. The correct answer is speed is the rate at which position is changing. And rate means blank over blank. And it doesn't say, but it's implied time. So it's blank over time, and position is the thing on top. So speed is how much position changes per time. Okay, going on to the next question. What is acceleration? Okay, we have 6 people. That's all that answered last time. So, move forward. Maybe I'll move forward. So we had this time 0600. That was unanimous. And acceleration is indeed the rate at which velocity is changing. So now, since it's a rate, what does rate mean? Okay, so it's going to be something over time, and that thing over time is velocity. So acceleration is the rate at which velocity is changing. It's the velocity divided by time. Final question of these 3. What is velocity? Got 5 answers. We've had 6 in the first 2, so somebody who's been answering hasn't. There we go. There's the 6th. Okay, so this time it was 1050. This one we all fell flat on our face on. The answer is one of the 2 zeros. It is D. Velocity is speed with direction. Speed is the rate at which position is changing. Velocity is the rate at which position is changing and the direction that it's traveling. So now we'll go into actually teaching what these things are. So speed, how fast you're traveling. We drive cars, we have a speedometer. Why? Because it tells us how fast we're traveling, it tells us our speed. Now that speedometer is telling us pretty close to an instantaneous speed, right? It tells me what I'm traveling right now. In truth, it's the average speed for a very short amount of time. I have a slide coming up later that talks about the difference between instantaneous and average speed. But your car speedometer is essentially telling you instantaneous speed, how fast you're traveling in a moment. We start in speed by just taking the average speed. Average speed is the distance traveled divided by the time it took. Now, this is written out in words. In words because, of course, we all understand words. Physicists like to write things short. We tend to be lazy people. And so we make symbols to make this simpler. So a physicist would generally write this as that. Now if I read that in my head, that has words that still go with it. That says V average equals delta x over delta t. Now that was just the only thing that was different than what you see probably was I said average instead of AVG. And you may or may not know the capital Greek delta. That's capital D in Greek. Delta always means the final value minus the initial value. Or, as we say in physics, the change in. So I could have said change in, what do you suppose X stands for here? Not speed. V, okay, let me start there. V stands for speed. And you're probably already kicking yourself saying, why in the world would V stand for speed? There's no V in the word speed. V stands for speed because really it comes from velocity. Remember, velocity is speed with direction. And so V stands for speed. And if I put V with an arrow over it, that's velocity. The arrow tells you that it has a direction to it. And so speed with direction is velocity. So the V with the arrow is velocity. The V without it is just the speed. It doesn't have the direction, just the magnitude. Remember, magnitude is the size, how big it is. So V in that equation was speed. Then X. X is, actually I'll put position. Delta X, the change in position, is the distance. Hence, distance traveled here, delta X there. Delta X is distance. X is position. So when I have delta X, that's the final position minus the initial position. And then, of course, pretty obvious one. What would this T stand for? Time. So it's a lot shorter and easier to write this equation. Okay. Yeah, there, everything fits. It's a lot shorter and easier to write the equation as this. But of course, when you're learning, it's going to be more meaningful to you to write it as the way with the kind of pukey yellow background color. That's the equation. Let's take a simple example. Let us suppose that it takes me 10 minutes. That's not it. 10 minutes to walk to school. What did I say the distance was for me to walk to school? The distance from here to my house? 3/4 mile. Now, of course, 3/4 miles as the bird flies is not exactly 3/4 miles as the roads travel. But we'll just still stick with it that my delta x is going to be 3/4 of a mile. What else do I need to find my average speed for that walk? I need delta x, the distance traveled. What else do I need? I have it up above, but I'm trying. I need the time it takes, and that's this number here. The change in time from when I start to when I end my trip is 10 minutes. So putting them in my equation for the average velocity, or average speed, excuse me, and I really am sorry, but I make that mistake. I say velocity when I mean speed. I say speed when I mean velocity. It's not correct, and I try to be really precise about everything in life, so it drives me crazy. So I'm trying to get better. My average speed is the change in position over change in time. So that would be 3/4 of a mile per 10 minutes. I can get this answer in miles per minute. 3/4 divided by 10 is 3/40. Miles per minute. If you want to put that in decimal value, we can. It's what? 0.075 miles per minute. Is this a standard unit for speed? No. No, it's not. So what is the unit for speed that you're most comfortable with? Okay, meters per second. That is the standard unit we use in science. I'm going to go to that in the end here. But before I get there, usually when you're driving your car, what are we measuring speed in here in the U.S.? Miles per hour. And so let's convert this to miles per hour. So I have V average is equal to 3 miles per 40 minutes. If I want miles per hour, my miles can stay there, right? That's the unit I want on top. But instead of minutes, what do I want on bottom? Hours. So I need a conversion factor that's going to cancel the minutes, so I'll need minutes on top, and put in hours on bottom. Now, how do you come up with a conversion factor? Well, the key is your conversion factor always has to equal 1. So that means I need to have my time in minutes is equal to my time in hours. Well, how can you relate minutes to hours? 60 minutes in 1 hour. Whoa. Okay. I was at the bottom of the page and my hand made it switch pages. 60 minutes in 1 hour. So I take this and just multiply through. Now, we don't have to be super geniuses here. We know that the zeros cancel there. And 6 times 3 is 18. Divided by 4 hours. If I take 18 divided by 4, that's the same as 9 divided by 2, which is 4.5. So I'm walking about 4.5 miles per hour. MPH means miles per hour. This here is exactly the same as that there for the units. Now the truth is, on a treadmill, I usually walk around 4.2 to 4.4 miles an hour. Walking on the dam out there, just moseying, I'm usually about 4 miles an hour. So the distance must be a little bit shorter than 3/4 mile, or it takes me a little longer than 10 minutes. Just in case you think, I really am striding out there when I walk home. So, what have I done on this slide? Number 1 was we had the definition for speed. Then we defined what the variables are. You'll need to know what those variables mean so that when you look at the equation on the equation sheet for the test, you'll be able to understand what the equation is saying so you can use it. And then I did an application to see how we calculate that average speed. And then finally I showed you how to convert units. These are all things we're going to do again and again, but you need to develop some ability with. Any questions before I move on? Okay, here is a page I made for unit conversion just to practice. So we have, let's say, 70 kilometers per hour. So I have V equals 70 kilometers per hour. And to be consistent, I'll put HR. The correct abbreviation for hour is, I believe, just H, but I didn't look it up. We never use hours, we use seconds. And so that's why I'm not positive on it. And I want to convert that to miles per hour. So if I want to convert that to miles per hour, what do I need to do? What did I do to convert my miles per minute into miles per hour? I found a conversion factor, and what that conversion factor have to equal? 1. So I'm going to multiply this by a conversion factor that equals 1. And what do I need on top? Actually, in this case, we're trying to convert it to miles per hour. So if I want miles per hour, what do I need on top? Miles. So I'll put miles here. And then my conversion factor, which one am I converting into miles? Then which ones? The kilometers. Kilometer is the correct pronunciation, by the way. I went 1 year saying kilometer in class, and I felt goofy every time I said it, so I stopped. So now I need to find a value that's equal to 1 that will give me that ratio. So I put on the left some what we call conversion factors, the equivalence between the top one is 1 kilometer is 0.6214 miles, the next one, 1 mile is 1.609 kilometers, the last one is between hours and seconds. Which one would you like to use as my conversion factor guide? Okay, so 1 and 1.609. Now I put here, I find it easier to multiply by 0.6214 than divide by 1.609. It doesn't make a difference, right? You could have chosen the lower one and it would have, or excuse me, the upper one, and it would have worked out just the same. You would have had 0.6214 on top and 1 on bottom. You get the same answer. Now when I multiply these, note the units. Kilometers cancels with kilometers. And so then I'm going to be left with how many miles per hour is 70 kilometers per hour. Somebody have a calculator? Okay, I'm going to write the 49 that you said. 43.49 miles per hour. Now, he brings up a good point. In physics, if we're taking a higher level class, we're really, really careful to not overstate our knowledge. 70 kilometers per hour. In physics, I would tell you, well, I'm not sure that could be 74.2 miles per hour. Because that 0 could be a placeholder, could be there just to make the 7 in that position. Or it could mean that it's somewhere between 70.49 and 69.51. Right? I can't tell you. It's what we call ambiguous. So I'm going to assume that that has 2 useful digits just to go to the larger one it could be. So if that has 2 digits, I don't know my answer to anything better than 2 digits. So I would typically just take this and round it and say, to the best of the knowledge I have given my starting speed, that's just 43 miles per hour. Now on your lab reports, which I guess you haven't seen yet, we had some people that measured like 1.2, 1.19, 1.21. All of these should have been measuring this digit here. Why do you suppose people didn't write anything for that digit? Because it was a zero, and they were thinking, well, zeros are meaningless. But if you measured it, it's not meaningless. If you put the zero there, it wouldn't have any point in being there except for because it's meaningful. So when you're making the measurements, if you have a trailing zero after a decimal, that's always meaningful. It's telling you, I know this number is zero. Whereas if you don't have it, that means I don't know what that number is. So there's a difference in the meaning. Okay, now I'm not going to belabor this point. It's not something we drive into at this level. But when you're doing your homework, when you're doing your calculations, keep all the numbers in your calculator. Don't like clear and then just put in the first two digits. But when you get to the end, don't put more digits in the answer than you started with. Right? If you started with 70, don't make your answer 1,563.29. Just make 1,600. Because you don't know the rest of that. It's calculated, but it's meaningless because you didn't know what the next digits were in your original number. Okay, I won't mark you off if you put a whole bunch of extra digits. It's just a nuisance for you to write it and a nuisance for me to read it. Okay, so we've converted this into miles per hour. Now let's go ahead and convert it, instead of miles per hour, into meters per second, which is the standard unit, which I was going to do with my walking speed and forgot to do. So start with our original number again, just to be fun. Whoops. How do I convert this value into meters per second? What do I have to convert? Okay, hours to seconds is one conversion I need to do. So I will do that first because it's the first one with this name. There are two conversions you might have gathered. So hours per second. If I want hours to cancel, where is it going to have to be? On top. And so then my conversion factor is 1 hour is 3,600 seconds. So there's my conversion factor for the time. But I also need to convert my distance. I had 70 kilometers. What unit did I want for distance? Meters. What's the relationship between a kilometer and a meter? It's what? 1 kilometer is 1,000 meters. So where do I want kilometers on my conversion factor? On the bottom, so it will cancel with those kilometers. So there are my two conversion factors. Now, of course, 1,000 divided by 3,600 is just 1 over 3.6. So really all you need to do on your calculator is take 70 and divide it by 3.6. And that's very slightly less than 2 or 20. So what is it? 70 divided by 3.6. Like 19 or 18?
Yeah, 19 or 20.
And so once again, I would just say that's wavy lines means approximately equal to 19 meters per second. Feeling more comfortable with the unit conversions? Now, another way that you might have seen this written, this is the way that my son has been learning in school, is to put and then you have your conversions like this, so you have Right? It's the same idea. It's just putting it in a grid instead of putting parentheses like I did. You still multiply everything on top, divide everything on the bottom. And as always, if you watch the units, hours and hours canceled, kilometers and kilometers canceled, leaving us meters per second. In the lower version, and then it leaves us meters per second. Okay, any questions about unit conversions?
Are you requiring us to know the unit conversions for like tests and stuff?
You don't need to know the conversion factors. Things like 1 kilometer is 0.6214 miles. No, you don't need to know that. But you need to be able to look at a list of these and know which one to use and how to use it. All right, we are totally on slide 10, which is an example to calculate average speed. Driving from Phoenix, Arizona from Kingman, Arizona to Phoenix, Arizona. Why would we do this? I don't know, because we want it to be hot. If we want to do something fun, we would go out here, where the Barringer meteor crater is, where you have a mile diameter crater created by a meteor impact. Well, it's not a meteor impact, it's a meteorite. Meteor is the light you see when it's going through the sky. Meteorite is the object that hits the earth. Okay, so that wasn't part of the lecture. Calculating the average speed. What is the average speed going from Kingman to Flagstaff? You don't have to give me the answer in like blank miles per hour, but in how I would get there.
120 miles over 2.4 hours.
That is correct. Okay, this uses HR for the abbreviation, so maybe that is the 120 miles is the change in position, the distance traveled. 2.4 hours is the change in time. And so then when I divide those two, of course, 12 divided by, 120 divided by 2.4 is going to be 50. Because 12 is half of 24. So that's 50 miles per hour. Now going from Flagstaff to Phoenix, we're on a different road, different conditions. What am I going to have for my V average there? $140 miles divided by what? 2.6 hours. So if you put that in your calculator, it's 53.8 miles per hour. Now I'm keeping one more digit than I started with because I want to show something at the end of this calculation. So I'm keeping one more than I normally would. I normally just round that to 54. Now, what about for the total trip? What's the average speed for the total trip? Okay, first answer I heard was Michaela. What did you say?
Are you just asking for the total speed?
The average for the total trip, the average speed for the total trip.
50 miles per hour plus 53.8 miles per hour divided by 2.
Okay. If I do that calculation, that will give me 51.9 miles per hour. Now let's compare that to what we would get if we used this equation for the average speed. If we used that equation, we would have had total distance is 260 miles. The total time is 5 hours. 260 divided by 5 is 52.0 miles per hour. Those are not the same. So one of those two has to be incorrect. I don't have a poll, but which one do you think is incorrect?
52.8.
The top one,
The 51.9 is the incorrect one. But why? I mean,
because you rounded for.
it's not a round-off problem. That is an obvious first thing to go to when you're close. Did you round off wrong somewhere? You cut off some digits. It's not a round-off. The two answers are clearly different if the numbers were more different. Like, let's say it took you only 2 hours in the second one, you'd have seen a much bigger disparity between the two.
Perhaps order of operations.
It's not the order of operations. Here's what it is. When we took the average as if these were just two equal parts. But they weren't equal parts. One of them was for a longer period of time than the other. So when we're doing the average, we would actually need to weight them based on how long they are. This is most clearly exemplified with the really silly problem. You need to drive from here to Omaha, and for argument's sake, let's say that's 60 miles exactly. Unfortunately, there's bad traffic for the first half of the trip. So for the first half of the trip, you only drive 30 miles at 30 miles per hour. How fast do you need for the second half of the trip to average 60 miles an hour? You might have heard this question before. It's silly when you get down to the nuts and bolts, but it sounds like a reasonable question when I ask it. What were you going to say, Tyler? You cannot. Why? Well, let's think about this. Our equation was V average equals delta x over delta t. And we have delta x total is equal to 60 miles, and the average needs to be 60 miles per hour. So using this relationship, I could just take this equation and solve it for delta t. Now, this class has a reasonably low mathematic requirement, so whether you're comfortable with it or not, I'm going to show how we take this equation and solve it for delta t. If you're comfortable with that, well, then I'm wasting your time, and I'm sorry. But if you're not, well, then it's beneficial, and that's why I have to do it. So if I want to get delta t, right now it's in the denominator. I need to move it to the numerator. So I will take my equation, and to get it into the numerator, I will multiply both sides by delta t. What I do to one side of the equal sign, I must do to the other side. I can't just do it to one side. And so I multiply both sides by delta t. You might ask, why, oh senor, would you multiply by delta t? Because I had delta t on the bottom, that's the denominator, and I didn't want it there. I wanted it to be on top by itself. So I multiplied by it on the bottom, so these two canceled out. I have delta t over delta t. It's like 5 over 5. What's 5 over 5? It's 1. It doesn't matter what the value of delta t is. If I have delta t divided by delta t, it's going to be 1. So now I have delta t times v average is equal to delta x. Now this is now solved for delta x. I can find the position, the distance it's traveled, if I know the time and the average speed. But I wanted delta t. So to get delta t by itself, I need to divide by everything it's multiplied by. So delta t is multiplied by v average, so I divide by v average. And if I do it on one side, I have to do it on the other side. So that gives me delta t, notice these cancel, is delta x divided by v average. Now coming over here to our problem. I need to travel 60 miles with an average speed of 60 miles per hour. How long do I have to complete that trip? I have 1 hour. Using the equation that we just worked out, I have delta t is equal to 60 miles divided by 60 miles per hour. Notice the miles cancel, and I'm left with 1 over 1 divided by hours. Well, 1 over 1 divided by hours, you probably remember the rule on invert and multiply when you divide by fraction. So that's equal to 1 over 1 times 1 hour over 1, or 1 hour. So, as Tyler said, we have 1 hour to complete the trip. Now let's go to what I told you for that silly little problem. For 1/2 the trip, so for delta x1 is equal to 1/2 the total distance, 30 miles. The average speed was 30 miles per hour. How much time did we spend doing that first half of the trip? We spent an hour. Using the exact same calculation, that's 30 miles divided by 30 miles per hour is equal to 1 hour. So we spent 1 hour in the first half of the trip. If we're going to get to Omaha in 1 hour and we spent the first hour in the first half of the trip, how much time is required for the second half? We're going to have to do it instantly. No time allowed. Well, that's not possible. And so that's why it's a silly question. When you start analyzing, it's simply not possible. Many people say 90 miles per hour because 30 plus 90 divided by 2 is 60. But that's not the way it works here. You have to take the distance divided by the time because you have to wait by times. Going slow, slow, slow.
Wait, I'm sorry, I
Go
still
ahead.
didn't understand why the two values, what was wrong with the two values before? You had 51.9 and then you ended up with 52.
Yes. Okay, the 51.9 was taking the average of two numbers, but one number was for a time of 2.4 hours and one was for a time of 2.6 hours. And so when you do the average, you actually have to do the average over time. So I have to take the one that's for 2.4 hours, multiply it by 2.4 over 5 to get the fraction of the total time that one is. The one that's 2.6, I have to multiply by 2.6 over 5 to get the fraction that one is. Then they would agree. Okay. Next slide. The only thing that I haven't talked about here carefully is the instantaneous part. Instantaneous, I said the speedometer measures an instantaneous speed. Instantaneous means that you take the average over an extremely short amount of time so that it didn't have time to change. It should be precisely an instant, but of course it's impossible to get a perfect instant. So you're bringing it down, so the instantaneous speed is how fast you're traveling now. Now if you travel from here to Omaha, your speed is going to vary, right? You're going to speed up a little, slow down a little. So your instantaneous speed is moving up and down. Your average speed is going to be, somewhere between the maximum and minimum speeds that you have on that trip. So when I was in calculus class, we did the mean value theorem, and I was like, well, that's pretty obvious. The average is somewhere between the maximum and minimum. Okay, this will be our last question. What does a car's speedometer measure? Okay, we had 0, 5, 1, 0. So we can just compare between average velocity and instantaneous speed. Instantaneous speed means how fast you're traveling at an instant. Average velocity is going to be the average speed with direction. Does your speedometer give you the direction? No. So it can't be a velocity. It has to be a speed. Now, if you have a compass in your car, you can combine the two to get a velocity. And it's instantaneous because it changes very quickly. Okay, remember the potential test question. If you don't have a form, I have more, lots more. And the homework is due today.